JNCIA series, Dynamic Routing Link State Protocols. Well, this is part 2 of a 2-part nugget series on dynamic routing. And in the previous nugget, we talked about the aspects of vector protocols. Here, we're going to see really the improvement on those concepts and actually something that we're going to be more concerned with moving forward, because the two main protocols we're going to be using for interior gateway protocols are OSPF and ISIS or ISIS, which are both link state protocols. Now, you might ask me, Michael, if that's the case, and we're going to be using link state protocols as our interior gateway protocol from here on out, then why in the world do we have to learn about vector protocols? Well, there's really two reasons. Number one is that RIP version 2 is still ubiquitous. It's still used a lot for a lot of small to medium-sized businesses. And we're going to be doing migration often from RIP version 2 to OSPF. So we still need to know about it. The other thing is this. Our exterior gateway protocol of choice, BGP, Border Gateway Protocol, is still a vector protocol. Yes, it's a path vector, but it's still considered to be a vector protocol. So it's important to know these differences. And these fundamentals in this nugget that we're going to look at are going to carry with you throughout your entire career as a routing specialist with Juniper routers. So in this nugget, we're going to look at the advantages of link state protocols, why we use them. We'll look at the adjacency concepts and what's going on there. We'll look at flooding, and we flood with link state advertisements. We'll talk about the shortest path first algorithm, how it synchronizes, and how the databases are calculated. And then we'll end up looking at areas. Now remember, almost all the concepts here that we're going to look at are fundamental to both OSPF and ISIS. And from a historical standpoint, really, OSPF is what we call the IETF link state protocol, and ISIS would be the ISO link state protocol. This is where we got the OSI model from. So if you think about it, this is really kind of more the commercial link state protocol of choice down through the years, and we see ISIS still used a lot in the government, in the military, some service providers. So these are very important fundamentals that we're going to look at here in this nugget. So let's jump right in and talk about the advantages of link state protocols. Okay, with distance vector protocols, we had some fundamental problems. We knew that they were slow to converge because of that routing by rumor thing and the fact that they only really understood the network based on information they got from their directly connected neighbors. We also know that they're vulnerable to loops, and there's several mechanisms that we talked about to help prevent those loops. So what we need is something that helps us converge quicker and have better loop prevention mechanisms. Remember, vector protocols use that kind of hop-by-hop distributed calculation of routes mechanism. And the more routers you have on the route or between point A and point B, the larger your network is, the longer it takes to converge. But think about this. What if, instead of having to perform a route calculation before we passed on the results of the calculation, a router in a domain could actually pass an update to its upstream neighbor as soon as it received it, and then perform a route calculation on a copy of the update after the fact? With this philosophy, our routing information can be sent to the routing domain almost as quickly as the routers can forward it. And so convergence can pretty much happen in all the routers at almost the same time. What if we could build this topology database, and each particular router in the domain or the area could have the same identical database? For example, what if, instead of using distance vector, this particular router right here, who only knows information based on its directly connected neighbors, like this particular router or this particular router, what if instead this topology database, this area of routers, what if each one of these peers, each one of these neighbors in this routing domain had a topology database where it could map out this entire area? Now, how do we gain this? How do we get this topological database, right? Well, here's what happens. Every router in the network is going to send these hello packets on its local links. So, for example, this router has this local link, and this local link. It's also going to listen for hello packets to discover its neighbor routers. Also, every router sends an announcement that identifies itself along with its directly connected links and its directly connected neighboring routers. So every router receives these announcements, and it's going to keep a copy of the announcement in a database. It'll also forward this announcement to its downstream neighbors. So when a router has a copy of an announcement from every other router in its database, it can then accurately calculate routes to its destinations. And this calculation is based on the Dijkstra algorithm, or the shortest path first algorithm. So bottom line, every router in the network must send an announcement that identifies itself, its links, and the cost associated with each one of those links. And the cost is going to be based on, for the most part, on the bandwidth. Let's see how this link state database gets built in this network with 4 routers. Obviously we have router A, router B, router C, and router D. So router A is going to say I have 2 connected subnets. I have 1.0 and I have 2.0, right? You can see them up here, 1.0/24, 2.0. Router B says I have 2 connected subnets. I have 2.0 and 3.0. Router C says I have network 3.0 and network 4.0 connected, and router D says I have network 4.0 connected and 5.0 connected. Then router A says I have 1 neighbor, router B. Then router B says I have 2 neighbors, router A and router C. Router C says I have 2 neighbors, router B and router D, and router D says I have router C. And this information is propagated to all of these routers using a combination of initial hello packets and link state advertisements. So every particular router in this domain has a topological picture of the network. And this is going to help us reduce that loop problem that we have with vector protocols. Remember, vector protocols, they only know about a network through its directly connected link and its directly connected neighbor. But a link state router knows the complete topology of the network, so it's less susceptible to those kinds of loops. And we call it link state because it uses a database to maintain the state information concerning all the links and all the routers in the networks. Now that's a pretty simplistic, idea of how link state protocols work. And again, the algorithm that we're going to use is the Dijkstra algorithm, or shortest path first. But there's really 4 fundamental concepts that we have to understand about link state protocols: adjacencies, flooding, that link state database, and then the calculations, how the router actually uses the information in the link state database to calculate its routes. We have to master those 4 concepts so that we can be effective at troubleshooting our OSPF link state network or our ISIS link state network. Let's talk about adjacencies. Now, as I was going back through and editing some of the previous information I delivered to you, I noticed that I had misspelled the word Dijkstra in the algorithm. It's actually D-I-J. I left the K out, okay? It's not okay to leave out the K. Dijkstra. And this person's name is actually Edsger, E-D-S-G-E-R. And he, by the way, he was a Dutch computer scientist, and he passed away not that long ago, back in 2002. So let's talk about this adjacency, because before link state routers can start sending announcements and receiving announcements and start building those databases that we talked about, they have to identify their neighbors. And it's not just enough to say, I know who's connected to me directly, okay? Because in some networks, a router, let's say R6 over here, might be speaking other routing protocols like Cisco's EIGRP, or RIP version 2, or even BGP. So a router that's running a certain link state protocol has to be able to find just those routers that are connected directly running the same protocol. There we go. Now really the concept here of adjacencies is we're trying to build this neighbor relationship. And that term can be used kind of loosely. However, for example, OSPF, it's actually much more of a specific relationship. 2 routers, let's say router 5 and router 4 here, these 2 routers. These 2 routers are neighbors if they should be exchanging route information in a common protocol like OSPF. And if they've identified each other, they've verified that the other is aware of themselves, and they've both verified that there's no condition that exists, no situation that would prevent the exchange of routing information. Certain things have to match on router 5 and router 4. Once they've agreed that everything that's supposed to match will match, then these neighbors are adjacent. So you could think of adjacency as like the next level up from just being a neighbor, okay? Two neighbors are going to, with those hello packets, they're going to make sure that they have all the metadata that they need that will allow them to share routing information. It's then at that point only that they can be considered adjacent. Very important distinction. Now, one of the main requirements of a link state protocol is that every router has to identify itself. And this is called a router ID or an RID. And that can be something that you manually configure. It could look like an IP version 4 address, or it could be derived automatically from an existing IP address assigned to one of the interfaces, or even better, how about the loopback address? All that matters is that every router ID is different than any other router in the domain. And it has to be pretty consistent. If I'm going to use the loopback address on router 2 to identify myself as to the other neighbors, I'm going to have to use that same mechanism to identify myself to all the neighbors, okay? Now, how do we identify ourselves? Well, we've already alluded to this. We use hello messages. I don't know if you saw, but there was a remake of the old Three Stooges, you know, the Three Stooges TV shows and movies they used to have, and of course, one of the things that the Three Stooges do is they go, hello, 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 hello. That's what's going on here. They're all kind of doing the Three Stooges mantra to one another. And by the way, in this hello message, it's going to include that router ID. There's also other information as well, stuff that's pertinent, such as timer settings, authentication information, interface parameters. Let me jot that down. Timers, authentication, interface params. And what's the goal here? Well, we have to make sure before we form the adjacency that these routers can agree, that they're compatible. It's kind of like, you know, one of those online dating services where they're making sure they have compatibility first. And what are the three areas of compatibility? How to exchange information? Can the information be transferred or exchanged reliably? And do the neighbors trust each other? Something else that routing protocols do is when they are enabled, they have some mechanism of specifying which connected links, a single link or all the links, which of them are included in the protocol operations. Well, link state protocols will transmit hello messages on those links at a certain interval. They can be broadcast messages, they can be multicast messages. They want to make sure that all the undiscovered neighbors can find out about them. Now, it's also important, another rule is if R2 sends a hello message to R1 and R2 sends a hello message to R3, it's very important that no hello message is ever forwarded beyond that direct link. So R1 is not going to forward R2's hello message, and R3 is not going to forward R2's hello message. Basically, the handshake was just for them. Now, one thing that will happen is that when router 3 sends a hello packet to router 4 and router 1 sends a hello packet to router 5, it's going to say, hello, I'm router whatever, RID. These are my known neighbors. Now, after all the neighbors in these domains create their adjacencies and they know about each other, from this point on, the hello packets that are sent are going to serve as keep alives to make sure that the link is alive, to make sure the peer is still there and operating. And one of the parameters that the router can include in its hello message is to say, how often am I going to send hello packets? Now, depending upon the link state protocol, this hello period between routers, it could be non-negotiable and predetermined, or the peers might be able to negotiate the hello period. And remember, we might call them different things, but these behaviors are going to be found in OSPF and in ISIS. That's why it's so important. Now, as we've determined, every router in our network, in our domain, has to get every announcement from every router and record a copy of that information into its database, right? That's how it gets that topology of the entire domain. Now, this process is called flooding. So each router sends its announcement to all of its adjacent neighbors, and then each of these neighbors forwards a copy of the announcement to all of their neighbors. Now, as you look at this topology here, we can see that we've got some loops, right? Well, we could consider using split horizon to stop the loops, which means you can't send an announcement back on a link that you learned the information from. That's split horizon. We could use that mechanism still with link state, but we don't, okay? Because a better process to give us a reliable flooding process, for example, when do the routers know when to stop flooding, are going to be aging, sequence numbers, and checksums. Now, to reiterate some central tenets of link state behaviors, the information in every router's database has to be the same ultimately as the data in every other router's database. R6 has to have the same database as R2. So no router can modify another router's announcement, and every router is responsible for its own announcements. Well, what happens if a router fails, for example, after it floods out an announcement? Maybe it's a link problem. The neighbors on the link will detect the failure through the layer 2 protocol. And remember, the way they detect this is they're not getting any hello messages, right? So all the affected neighbors are going to send out new announcements that indicate there's a change in the topology. But here's where our problem comes in. If router 6 over here fails, non-adjacent routers like router 1, router 3, and router 2 will receive an announcement from router 5 and router 4 that A is down. But these routers still have A's link state announcement in their databases, right? So what should be done with those? Well, link state protocols, whether it's OSPF or ISIS, has a field in that link announcement known as age. And when a router sends out an announcement, it sets a value in this age field. And then during the flooding process, this age value, depending on the protocol, will be either decremented, go down, or incremented, go up, by other routers that are flooding. So eventually, this will be declared aged out or invalid. It'll get deleted from the database. An origination of a new announcement that has a whole brand new reset age is a refresh. So eventually, that announcement that was sent by router 6 before the link went down will age out on router 1, router 2, and router 3. And so these routers will assume that router A's or router 6's link is down until they get some type of refresh message. Let me clean up my screen here. Now, by the way, you won't have to know this until you get to the JNCIS level, but OSPF is actually going to increment that age value in the field, and ISIS is going to decrement. So inc, dec. That's not test worthy for the JNCIA exam. We're actually kind of, building a foundation right now for JNCIS, to be honest with you. But this is stuff you would need to know when you go on the job, the behavior of your link state protocols at Nugget Lab. So we talked about aging. The second thing was the sequence numbers. So what's going on here? Whenever a router gets an announcement, it'll send a copy out each of its downstream interfaces. So this can be replicated a bunch of times. This is a network that only has 6 routers in it, but imagine dozens and dozens of routers. So some of the routers are going to receive multiple copies of the same announcement. Well, what happens if they arrive at the same time? What if there's some delays or outages? And accepting an announcement that has the lowest age, that wouldn't be a really good way to do it. Age isn't a really good method for choosing the most recent announcement because there can be other problems in the topology, outages, there can be bottlenecks. So a second value, the sequence number, that's going to say this is the most recent version of a router's announcement. So if you have 2 announcements that come to the same router, okay, let's say to router 4 here, the sequence number value that is higher, that'll be considered the newer information. Kind of the same way that when DNS is doing a database replication. Now there is an issue if a router restarts, okay, or it does a reload, it loses all the memory, it loses what the last sequence number was. So there are some issues. And we'll learn more about that when we get to the JNCIS level. Now there's also checksums. I mentioned that was the third method, part of the flooding process. There's lots of ways that a link state announcement can get corrupted. There could be just noise on the wire. It could be part of the router's database corruption. So there's possibilities of that announcement being altered. So a checksum is performed over the entire contents of the link state announcement with everything except for the age field, okay? Because the age field changes as it passes from router to router during the flooding process. And that recalculation would mean that it would be different every time. So it does a checksum as it goes across routers. And that's important. Okay, our next major concept is database synchronization. Let's check that out. Okay, so far so good, right? We've established the fact that the announcements from all of the routers in our network are going to be flooded. Every link state router will store a copy of the most recent announcement from every router, including its own, in its database. We saw how aging is used so that what we call orphaned announcements won't be kept in the database on an ongoing basis. the age of every announcement is being tracked, and if the originating router doesn't refresh the announcement before that limit, it'll get deleted from the database. Now, when a new link state router, let's add one over here. Router 7 comes into the network. It's going to flood its announcements to update all the other databases and all the other routers. But how does this router build its own database? I mean, we could demand that all the other routers reflood their own announcements whenever they see a new router come into the domain, but that would be pretty inefficient. And it's also not scalable once we get beyond, 10 routers. But we still have that mandatory aspect that says every router has to have the same database. So how do we allow a new router to come onto the network, build its database without requiring extensive reflooding on all of the other neighbors in the domain? Well, here's what we do. After the router forms adjacencies with router 6 and router 5, right? You've got router 7. It forms its adjacency with these two routers. It initiates a process known as database synchronization. That's what we're talking about here. So two routers, let's say router 7 and router 5, will synchronize their databases. Then they'll describe what's stored in their databases to one another. If a router sees through its neighbor descriptions that a neighbor has one or more announcements that are not in its own database, then the router can request that the neighbor send a full copy of the announcement. So the router can synchronize with its neighbor and feel pretty confident as a complete and consistent database. And one of the things about these protocols is that they have what are called announcement headers. What does that really mean? Well, that really means that there's a lot of different types of announcements. There are certain identifiers that are associated with the link state announcement that other routers know this stores this kind of information and this stores this kind of information. So sometimes, for example, in the link state synchronization process, all that has to be examined by the neighbor router is the information stored in the header. So only the header has to be sent during the synchronization phases when a neighbor is describing announcements in its database, and when a router is requesting a copy of the announcements that it doesn't have. Only the headers. Brilliant. Okay, so we've tackled the issue of what happens when a new router comes on and how we prevent the reflooding process. Now we have complete databases. Our routers can now start calculating, using the Dijkstra algorithm, the shortest path to all the other routers in the network. So using that database, every router, router 1 will create its own shortest path first tree. So will router 2 and router 3 to all of the routers throughout its own domain or area. Now, the rules that we deal with here actually comes from what we call graph theory. So the shortest path first algorithm is used in lots of other disciplines. Okay, it's actually a mathematical theorem, and so it wasn't like created just to be used by Juniper or Cisco routers. Okay, it's used for a lot of things, but we're calculating the shortest path based on the root of a tree. So each one of these routers is the root of their own tree, and they're calculating the shortest path to a destination network or prefix. Well, in order to do this calculation, we have to assign some type of value to these links, right? Because what does shortest mean? Well, we know that in link state, shortest doesn't mean the number of hops, okay? Or the number of paths, like we would see in BGP, or the number of hops that we see in RIP version 2. Here, we have a cost that is assigned to every one of those links. So this cost method is what we call a dimensionless approach. Each number represents the cost of sending a packet out the interface of the link, and that's very important. Remember this going forward. Listen carefully, write it down, okay? Cost, okay? Each number which is assigned to an interface, router 5, router 1, and so on, represents the cost of sending a packet out, egress, of the interface connected to the link. So a shortest path is the one with the total cost of all of the outgoing interfaces from the source, let's say router 2, to the destination, router 6. And as you can imagine, since this particular cost is some type of mathematical value, right, we could manipulate it. We could change it. We could assign higher costs to different links to influence the behavior and the way that traffic flows across our network. Now remember, in the initial hello process and the advertisement process and creating adjacencies and building the database, our router, for example, router 1 now has a link state database, okay? And it has information, for example, like the router IDs. Here they're simple. They're R1, R2, R5. But also it knows, based on the information it received from the routers, the costs that have been assigned to all of the directly attached links. So in the database it would have, like, say, R1 to R2. The cost is 1, right? Because R1 to R2, what's the cost on the outbound interface? It's 1. And it would say, R1 to R5, router ID to router ID, what's the interface cost? Well, it's the outbound, it's 2. Okay, so it builds this for the entire topology. That's the link state database. Okay, then what it has, this is what we call the first set. Okay, the second set, this is kind of like tennis, right? The second set is the temp database, or also known as the candidate database. In this phase, links are copied. Oh, by the way, let me mention this. This is how the tree is being built here. At the root of the tree is R1, right? Because this is basically R1's process. Itself has a value of 0, so its cost is 0. It costs 0 to get to itself, so it's the bottom of the tree. Let's make that clear. Okay, so the temporary database, the links get copied from the link state database to this particular candidate in a certain order, where they become candidates to be added to the tree. So once this list of candidates becomes empty, then our calculation is finished. That's what we're talking about here, the SPF calculation. So the goal of phase 2 is to basically empty out the list of candidates to build that tree. And so the third phase, or the goal, is the tree database. And the tree database is what we actually use in a link state protocol to find the shortest path from, let's say, router A to router 4. Our final concept deals with the concept of the area. As you can see from earlier, as our link state network gets larger and larger, okay, we only had less than a dozen routers, but if we get to hundreds or thousands of routers, think about that overwhelming process of all of the flooding and all of the scalability issues of building that link state database for all those routers. Flooding is an issue here, because the more routers you add to the network, then you're going to have a lot more announcement refresh activity. And the link state database becomes a scalability issue in a large enterprise network, because all of the announcements from all of our routers have to be stored and then used as part of that Dijkstra shortest path first calculation, phase 1, phase 2, and phase 3. Remember, the link state database, the candidate database, and build the SPF tree. Another factor is that all the routers in the network have to maintain and process the same exact database as all the other routers. Remember, the same topology. So if you have, let's say, dozens of high-end Juniper Core routers, and then you have, let's say, a couple of low-end, low-memory, low-powered routers, well, the performance of your entire network is kind of brought down by that one low-level router. So the weak link can really dramatically affect that maintenance process and scalability. So how do we deal with this link state scaling problem? Well, we do it by breaking up the network into areas. Okay, so within the areas, you can see here that by default we'll have the initial area 0 or backbone area. And by the way, from the standpoint of the JNCIA exam, all we care about is really area 0 or the backbone 0 of OSPF. So when we get into our configuration lab here coming up very shortly, all we'll be doing is configuring a single area OSPF routing environment, okay, not multi-area. That comes along later in the JNCIS and beyond. However, with areas, we got areas 1, 2, and 3 here, all within this autonomous system, or we can call it our administrative domain. All the routers in one area, let's say area 1 and area 2 and area 3, they have to have the same identical link state database. So each area has to have an identical link state database. Then the flooding of individual router announcements. Okay, so that's a certain type of link state advertisement, but the flooding of individual router advertisements is limited to the boundaries of an area. So when router F is going to send out individual router announcements, it's not going to get past this router. Same thing here, same thing here. Now, we can also have other processes like summarization, and we can also have the distribution or redistribution of routes from some other external routing domain like EIGRP, Cisco's proprietary protocol, or RIP version 2, or ISIS, or even another OSPF domain. We can distribute routing information from one domain to another, or from one autonomous system to another, so that they can learn about routes that are external to their own autonomous system. Okay? And that's what you're going to have to master as you move forward in your path to the JNCIE, okay, the JNCI expert, right? But we've got a long way to go before that. So you've learned now fundamentally the behavior of link state protocols, and I've done it kind of in a vendor neutral fashion. In other words, it doesn't matter if it's IETF's OSPF or the ISO's ISIS, doesn't matter. You've learned the behavior of those two protocols. You know all you have to know for this exam, and now you're quite ready for when I deliver you my JNCIS series coming up next. You'll be ready when I start talking about OSPF and ISIS, because you know the behavior of link state protocols and distance vector protocols, and to an extent, BGP is a path vector protocol. Awesome. In this nugget on link state protocols dynamic routing, we learned 5 key topics. We learned the advantages of link state protocols or algorithms over distance vector, talked about adjacencies and how those happen, the flooding process, SPF synchronization database calculation, and then finally the importance and the need for having multiple areas in a link state protocol autonomous system. Well, now that you understand dynamic routing and static routing, we're ready to move on now to routing policy, which is really going to be our last lecture-based nugget before we get into our deployment labs. We have a RIP version 2 deployment lab coming up, an OSPF deployment lab coming up, but we have to talk about routing policy first, because configuring routing policy is part of our labs. So we have to understand what it is and how we do it, okay? Well, that being said, I hope this CBT nugget was informative for you. I want to thank you for viewing.